This is Chemistry 302, Lecture 11 on weak acid-base calculations. In this lecture here, we take a look at what is probably the most common of all the different kinds of acid-base calculations you do. The calculation you do when you throw a weak acid or a weak base into water. I'm actually going to spend some time deriving the weak acid-base calculation from the Rice expression and teach you a little bit about it in perhaps more detail than you might want to know. But I do so because this is an introduction into being able to think in a more sophisticated way about how it is that you can understand acid-base equilibria as more than simple raw, do the calculation, you get the result. The reason we choose to do this with acids and bases is that we've given to weak acids and bases, is that we've taken a pass on looking at strong acids and bases and really understanding them. I mean, if you think about it, back when we were looking at strong electrolytes that were soluble salts, things like sodium chloride, what I said to you then was, let's throw some sodium chloride in water and let's assume it dissociates completely and makes 100% sodium ions and 100% chloride ions, and that KSP is infinity. And then, of course, we all roll our eyes because that can't possibly be the case. And then I even told you about how to do this calculation where you could go home and do some experimentation and figure out that the KSP of sodium chloride was maybe 5 or 10, not infinity. A big number, but not infinity. Well, then we roll forward, and it was time to take a look at strong acids and bases. And I talked about the analogy to soluble salts and about how we assume that KSP is infinity for a strong acid. But did you ever notice me stop and roll my eyes and say, we of course know that's ridiculous. We of course know that that can't possibly be the case. Oh, heck no. Instead, I just ran straight forward and said, throw HCl in water and it becomes all H+. Throw NaOH in the water and it becomes all OH-. I made this immediate assumption that it dissociates completely when we know that's not possible, and I came up with this great calculation that the H+ concentration is Ca and the OH- concentration is Cb, and I said, have a nice day. I did that because to really understand the truth of these high concentration strong acids takes us into an area of non-ideal behavior that's way, way too complicated for freshman chemistry, so we just pretty much give it a pass. And instead, we move on to weak acids and bases, which it turns out are operating in a concentration regime which is much, much smaller. Down with concentrations of 10 to the minus 5 molar, 10 to the minus 7 molar. At that point, the non-ideal effects aren't nearly as important, and so we can start to do a more rigorous treatment of what our weak acids and bases are doing. But as I begin these lectures, do understand that I've given a pass to strong acid-base stuff. Basically, we've just lied to your face about that. And now we've moved on to weak acids and bases, where I'm going to grind your face into it like you cannot believe. I want you to understand that going in so you can appreciate why it is that we're going to spend so much time struggling with acid-base chemistry, because this is the first place where we can really sink our teeth into the truth of what's taking place in acid-base behavior.